And thank you everybody listening now and also in the YouTube channel. So today we have the pleasure of having Professor Denis Burgarella from the Laboratory of Astrophysics in Marseille, in France, LAM. Professor Burgarella is an expert on galaxy formation and evolution, especially early galaxies, especially the use of space-based data, with emphasis on the analysis of galaxy spectra over a wide range of wavelengths. He did his PhD at the University of Nice in France, followed by postdoctoral work at LAM and the Space Telescope Science Institute in Baltimore in the US. He led the development of a computer code, CIGALE, aimed at the analysis of photometric and spectroscopic data from galaxies. And this code has been extensively used by our community, so I imagine that most of you will be familiar with it. Denis served as president of the French Astronomical Society as well as IAU Division J, Galaxies and Cosmology, and especially dear to our hearts is actually he was the father, the promoter of IAU Commission J1, and he was president of that commission. So in a way, he's responsible for this series of talks. So today he will tell us about his recent work on high redshift galaxies with James Webb CEERS data in combination with a new version of CIGALE, exploring a sample of galaxies with spectroscopically derived extremely low dust attenuation, GELDAs. So thanks so much, Denis, and yeah, take it away. Thank you.
Thank you very much, and thank you very much for inviting me to give this talk. Just a small correction, I initiated CIGALE, but now I call it CIGALE with Frederick Boken, who is one of the people here listening.
Okay.
But yeah, yes, I will talk about some results that I recently got from JWST. That's a paper submitted to Astronomy and Astrophysics. It's done with several people in Marseille and the CEERS team. Guy is still Frankenstein. And well, actually, that's an international collaboration. So this is the outline of the talk. I will move from several of them, and it's mainly related to metals and dust, and what are the dust and metal related questions that we have in the early universe. Early universe here means something above, let's say, 8, 9, but I will study galaxies at lower redshift as well. Okay, so this is an introduction. You know pretty well about it. We have only a small ISM mass in dust, but this is very important, at least for 2 points. First, because of the attenuation and reddening that we have in the spectrum of galaxy, and this energy is re-emitted in infrared as 700 wavelengths. But also, in another way, it helps cooling the ISM to form low mass stars. And these 2 points are very important to understand if we want to better know what happens in galaxies at all times. So I don't know if it's useful to for the audience here to know what is a dust grain, but I guess you know. So you have dust grain with a size, and this is something which is formed in dense and cool environments, like in the atmospheres of radiant of supernovae. Then they are released in the ISM. And also, you can have some grain growth in the ISM above a given metallicity. This type of formation of the helium-2 here on dust grain is also very important here, where the helium-2 can provide some cooling for stars at all masses. So grains are very important. Just now a parenthesis about something which is strongly related to dust. We have a project called PRIMA, that's a 1.8 meter telescope with 2 instruments, a spectrograph and an imager. The gain is huge because we have some cooling at 4.5 K, and the mapping speed that you can see here is very large, with a very strong improvement comparable to what we had before, like for Herschel, for instance. PRIMA has been selected for phase A study, and there will be a new selection at the beginning of 2026 to launch around 2031. 2 projects are in competition. And we'll have a conference in Marseille at the end of March, beginning of April, on the science related to PRIMA and infrared, that you are welcome to attend if you want to. You can still register. So let me now show you what is the life cycle of dust. So you start by star formation, of course. The star formation leads to the formation of stars, as you expect. And stellar evolution can provide you with 2 things. First, metal are formed in the stars and are expelled in the ISM, mainly via AGB stars and supernovae. So these two processes at the end of the lifetime of stars form this stardust, and the stardust goes in the ISM. If the supernova explodes, you can have a reverse shock that destroys some of the grains. It's expected that a lot of this dust grain will be destroyed, 90–95%, and you are left at the end with some dust in the ISM. As I mentioned before, if you go above a given metallicity, there's a paper by Asano et al. In 2013, you can have some dust growth in the ISM that contribute to the dust mass a lot. This goes back to the molecular clouds, and you can also destroy these grains by aspiration. And you finally get a loop here, which is a life dust cycle. This is inside the galaxies. But you also have, if you assume that the blue line is a galaxy, you can also have outflow and inflows that can change the dust and the metal contents in galaxies. So we try to understand all this life cycle of dust in the low redshift universe. But of course, also, we would like to understand what happens in the high redshift and for the first dust grain in the universe. Just to understand what is the origin of those grains, whether it's due to stardust or to ISM growth, we can have some criteria. For instance, in the Prima telescope, the imager provides some polarization instrument from about 80 to 260 micron. And from the ratio of the polarization between two wavelengths, this is the two wavelengths ratio, you can have some estimate whether the dust are coming or created around stars in the circumstellar media, or if they are due to ISM mixed dust models. And this polarization is very efficient, and you can get this ratio. So that's a way to identify what is the origin of dust. However, this type of detection will be limited to medium range redshift, around 4 or 5, maybe a bit less. So we cannot use this method at the moment at very high redshift. One of the points that I mentioned before is that dust can play a role in the transition from population 3 to population 2. So we know that the formation of the first low mass stars couldn't be dominated by the cooling from carbon oxygen through fine structural emission. And for this, we need to have some amount of carbon and oxygen, and therefore a critical metallicity that could allow to have fragmentation and a transition from lower mass population to stars. This value is still debated, but it's in this range. But as you can see here, you can only have this type of cooling here at low density, which means that if you follow the Jeans masses, you only reach high stellar mass, around 100 approximately. So you would like to get lower mass stars, different way to do that. So this is the first one. And we know that collision between gas and dust grains can also cool the gas and lead to fragmentation. And this happens at larger density here. So you have the cooling here, all these lines as a function of metallicity. And the other cooling is seen here. It's due to dust. And this time you can get lower mass stars that could be characteristic of the population 2 and later on population 3. So identifying this, if they are dust grains in the very early universe, is important because we might have some information on the type of population that we observe in this range. This is something more elaborated about the same structure with the contraction, the H2 cooling, the Jeans instability, which are presented here, the three-body reaction to form H2, etc., and this fission. But that's the same information that we have here. Now, once we have this information, we want to go to the life cycle of dust at high redshift. We know that a large amount of dust have been detected at very high redshift. You have here at least 4 papers, but it's still evolving fast, up to redshift 8.3 with relatively large dust masses. And these dust masses are very difficult to explain. If we look at what we have here, we have this diagram for NIRSpec and Michalowski, 2023. The bottom one is where you have the formation of dust grain by AGB stars. This is a redshift from 6 to 8.5, and this is the dust yield by stars. And these dots here with different colors are different galaxies in this redshift range with different properties and specifically different IMF. As you can see, we cannot explain these objects, the dust mass in these objects, via AGB stars. So we move to another possible dust formation, which is from supernovae. You have the same thing here with dust formation, and now you can reach these type of objects here in the redshift range that we have. However, the dashed line here, or the striped line, is where you expect to have the dust destruction after reverse shocks. That means that you might be able to reach this level with the supernovae dust, but soon after you will decrease. So maybe there is a factor related to the evolution of dust, and you can pick these objects in a small time range to be able to get this, and then they will decrease. So we don't know, and something we need to model. Other parameters like the IMF, for instance, could be very important. The red is top heavy, Krupa, salpeter, but that doesn't change a lot. There are new models that study this. So assuming that we cannot reach these objects with stardust, either AGB or supernovae, we need to find another way. And the most popular one is the hypothesis that we have large dust mass due to dust growth in the interstellar medium. So this is another diagram that shows the same thing. So you have the time since Big Bang, the dust mass. The supernova dust start very early. So you have dust very early that could be explained for these very high redshift galaxies. And the AGB stars produce dust by later on. So when looking at the universe below 400 megayears, so that's very high redshift, you don't expect AGB stars to produce dust. It has to come mainly from supernovae. So the points that we have here might be due to this dust growth. So assuming this hypothesis that I call H0, we can wonder if this is true, we should also be able to identify the galaxy without ISM-grown dust. So only this type of galaxies here, which would be different because they would have a much lower mass of dust. So if we look again at this life cycle of dust, that means that everything that we need to, that matters here is only this part of the dust cycle. You have production by supernovae, and eventually, or probably dust destruction as well. And you need to explain the highest redshift objects only using these type of things. Some papers suggest that you can have earlier dust formation around AGB stars for low metallicity stars, but still it's a bit difficult. Let's move now to JWST results. We know that we have some results that came very recently due to the deep observations. And one of these results is that we observe too many UV bright stars at redshift larger than 910. So this is the paper from Filkenstein et al. You have the absolute UV magnitude. Here you have the number of galaxies per magnitude and per cubic volume. The models here in thin lines, gray lines, are the pre-launch prediction at redshift 11. And what we observe with different projects are the red and the red symbols. So you see that we are above these predictions. With an evolving deep density function here at redshift hint, you would reach this region here, which is one possibility. And we study also different types of predictions. In this paper and other papers, we found out that there are some possible explanations. The first one is that the star formation efficiency could be higher, and that would produce larger UV luminosity for these galaxies. Another one is that we have almost no dust in these galaxies that, again, would help detecting UV galaxies. Finally, we could also have a top heavy IMF, which change, of course, the number of massive stars, and again, would be able to produce that. Earlier on, we had some also probabilities that the strong stochastic star formation could be at the origin of this, but it seems not to be popular so far, not able to reach this level. So we are left with several explanations. There are non-exclusives, that can be several of them, or only one, we don't know. And we would like to understand this. The most recent results seems to suggest again that we have this type of things, maybe for different stellar masses, but still we don't know. But we'll come back to this later on in the talk. For this paper, this work, I tried to estimate for my sample of galaxies from a project called CEERS. I will have the sample after that, and try to estimate Mdust. To estimate Mdust, you know very well that you can use different version models or modified blackbody, optically thin, optically thick. And all these models have constraints. Sometimes you have only one data. Sometimes you have a very good sampling of the infrared density. And this is one of the main issues when estimating Mdust. To control the link between the luminosity and the dust mass, you have to make an assumption of this dust mass absorption coefficient, kappa 0, and the beta red genes as well. So you have to make assumptions, and these assumptions are not very well known. We can get this from the fit, but it's a bit degenerate with the dust temperature. But still, we can have some information. So in a paper in 2022, not 2002, we tried to look at this type of thing. You have here the specific dust mass divided by Mstar, and the specific star formation rate. It's color-coded as a function of the age of the galaxies here, and as a function of the stellar mass here. What you can see is that you have less and less specific dust mass for older objects here, the youngest one being at the top. And you might also have an evolution with dust mass for these symbols here. But you have other ones which are here, the diamonds one, that are dusty star-forming galaxies that are out of this trend. But for all the other one, you seem to have a main trend, which is presented here, that is found also in the local universe. However, when you want to estimate the dust mass, you have several parameters, and the lines that you can see here, well, maybe I could go here, that's the same one, depend on what assumption you have. This one here is a Dren-Henley dust emission that we have in CIGALE, that's the baseline in the plot, and you are right in the models, in the data here. But if we assume something different, this one, for instance, assume an optically thin bibody with this kappa 0, this value. This one corresponds to the same dust absorption coefficient, no, a different, sorry, dust absorption coefficient before the reverse shock, and this one after reverse shock. So if we wonder if we can safely estimate dust masses in an absolute way, from this data, it seems that we cannot probably get that. Well, in this redshift range, at least, you might need other constraints from other observable. But using this data, you are left with some uncertainty on the absolute level. You still have some relative values that you can work on, giving the assumptions that you have. So this is one of the limits for all the studies. So in this paper that I submitted at the beginning of the month, I tried to work on understanding what are the first dose grains in the universe, and if we have maybe one of these population of galaxies with extremely low dust attenuation that I call GELDAs in this redshift range. That's a paper with all the authors that are here from the CEERS collaboration. So let's start from something that we saw before, the ALPINE paper in a redshift range, which is about, well, the bottom one is about the same, not the IOTS one. So in this paper, you have the wavelengths and the flux density. We have about 80 objects with some stacking in this region and also some data here. Because we have a redshift range between 4.5 and 6.2, a single observation at, for instance, 1 millimeter will change in the rest frame wavelengths, and getting different objects allow to cover this part of the spectrum for the infrared spectrum. The other one comes from stacking, and we have upper limits here. So all in all, we have quite a good statistical representation for these ALPINE galaxies of the infrared spectrum. And this is valid for this ALPINE sample, so this redshift range. And it's mainly for Lyman-Break galaxy, UV selected galaxies, so galaxies that are specific for observation from the UV side. So in the papers that I mentioned before, this one, we have about the same type of selection. And part of them are also the same type of redshift range. So we will make the assumptions that the infrared spectrum coming from this sample, which is very well, as you can see, sampled, is also used for the CEERS sample. This means that if we know, or if we fix the shape of the infrared SCD, and we assume that we have an energy balance, the only thing that we need to know is how much energy comes from the UV side into the infrared side. So basically, what is the dust attenuation in galaxies? And this is some information that we can get from JWST spectra. It's a strong assumption, but given that we have the same type of galaxies, I don't have time to go in detail, but we have the same stellar mass, the same type of beta, well, the same type of observable. I think it's something that could be relevant for this study. We have also some infrared data from SCUBA2 and a bit from NOEMA, but they are not very constraining. They are well above the detection limit. To try to constrain what we can do with that, we use the mock facility in CIGALE. So you fit the observables, so the spectrum and the photometric data with CIGALE. Then you create what we call best model. You add noise on this best model, the observable noise, and you refit the data with exactly the same parameters. And this allows to get some information on how well you're able to measure whatever parameters given the observable constraints. It's a bit different from the uncertainties, and that shows in this case here. So we try to estimate Mdust in and out. We have different dust masses. This is larger than 10 to the 6 in between and below. And this diagram using the Mark analysis suggests that we might be able to estimate dust masses up to or down to about 10 to the 5th solar masses, which is some information. Of course, you have uncertainties, and it might be a bit below or above, but we could get some information. Again, this is related to different parameters, for instance, to the stellar mass. So that's the same dust mass here that we get from CIGALE using the dust attenuation. And you have here the stellar mass. And the limit lies here, which means that we have some galaxies at the bottom, at the top, with some large dust mass, relatively large, then intermediate and low mass dust masses that are here. And as you can see in this range here between 8 and 9 in logarithms, we have a very wide range of dust masses, which means that the dust mass is not the only leading parameters to estimate these dust masses. When trying to understand why this produce these results, we looked at what data we have. We have JWST NIRSpec spectroscopy. And for most of these galaxies, we have the Balmer decrement. Well, of course, at high redshift, we don't. We also have the UV slope that we measure from the data. And we try to see if this dust attenuation in each alpha from the Balmer decrements or from beta UV correlates with the dust mass we estimate. As you can see, there is an excellent correlation between this and the Balmer decrement, or the each alpha, which means that the spectroscopic information is crucial. The crosses here are AGNs that I marked, and the colors means different dust masses. So UV slope is also useful, so you have the statistics above, but less than the Balmer decrements. And you can see that we lose this correlation at low beta UV here, where you find the same degeneracy. This can be due to different things. Well, first, because we are not able to model very well the spectrum in this range, but also physically, we might have different redshifts, different types of stellar population, etc. But still, we have, as you can see in this histogram, a very good difference that suggests that using everything, the beta UV, the Balmer decrements, and the rest of the spectroscopic and photometric information, we're able to get some constraint on the dust mass. Let me move to the spectroscopic data now. Why do we need spectroscopic data? First, for redshifts, you have here one of the first dusty star-forming galaxy, the SFJ1, from a paper by Zavala et al. And there is another one which was in a paper from Donan et al. And you see that if we have only the red frame UV or optical part, we get redshift that are different from getting everything. So the blue and the red one. So the redshift without the infrared information would be very large, while it would be around 5 if you use the total information. This is due to the fact that you produce with the dust attenuation, but also because of the strength of the line, some apparent Balmer break here, which is not related to redshift. And we really need to do a serious job when estimating this photometric redshift. If you do that too fast, you can get very wrong and get very wrong redshifts, as we saw at the beginning during the first phases of the JWST observation. I have several videos that can explain this. I will show one. It was really done for the public, so you have a lot of stars and stuff. So, but if we move, I don't think I can move it here. No. So we need to wait. So this is a paper by Pablo Arevalo, Dickinson, Steve Regnition, and several peoples. So the first of this galaxy, CEERS 93316 spectrum is here, where we saw this break was interpreted to be a redshift of 16. And you see the apparent break here, where you don't detect, and you detect the galaxy on the right. But after some point, we get some DDT, and we had the observation, spectroscopic observation. And using the model here, where you have the redshift, you see what happens. So you have the UV emissions, the dust emission, and the redshift is evolving here. And these are the observations in dark and the models. So you see that the models produce a Lyman break, which is increasing with redshift. And at some point, when the redshift increases, the dots, the models, get below the detection limit, and the Lyman break moves to the right. Well, we know that very well. If I can, no, I cannot. So you will see that what's happened, and at some point, we will have an agreement with a redshift, which is around 16. This is 4.5. Yeah, about here. So we have a good agreement photometrically, but then after that, of course, the redshift is too large and you lose the agreement. So that means that redshift, photometric redshift cannot be this one. So we move to until 20. Then we go back and we'll see what actually happens. So we come back to the redshift 15.5, which is the photometrically best redshift if you don't use any constraint from here. There is a good match photometrically. But we had spectroscopy, and we see that we have this line, each alpha, O3, each beta, and we don't observe anything, which means that the redshift is wrong. It's not 15.5. And that was one of the first results from JWST. We were not able to confirm the ultra high redshift that we get up to redshift 20 or even more using spectroscopic observation. So this is why we need spectroscopy for redshift first, but also because it provides some physical information. So let's the animation move to the end and we'll see the observed spectrum, which is well connected to the modeling that we had with CIGALE or anything else. You see the hot two triplets, each beta, each alpha here. And the observation perfectly match this. So we confirm the redshift is 4.91. We have quite a number of these galaxies in this range. So let me skip this one. And now this is what we have. So the redshift range from the CEERS observation, we had a lot of spectra, 1,337, 634 with the prisms that we used. We had some scuba 2 observation, and if we only keep the objects with a good redshift at larger redshift, redshift larger than 4, we had 173 objects in this range. As you can see, most of them are here, which is why I told before that it's in consistent with the partially consistent with the ALPINE sample. And so we use CIGALE to fit all these spectra. You know that we have NIRSpec with an array of microshutter, and you can select individual microshutters to observe the galaxies. And for instance, this one has been put here. So in 3 different wavelength range, this is a scale 0.2 arc seconds. So that's 0.2 approximately this side. And you move the slitlet up and down to get the background. So this is very efficient. And if the galaxy is not too large, you get a very nice spectrum. So I won't show all the spectrum. So we have different samples. So this is the one where you have the spectrum here. So let me just look at the right. You have the spectroscopic data, the photometric data from NIRCam, the infrared and simulated data here, and the best spectrum from CIGALE, using both information simultaneously. Another one here, redshift 6, redshift 4. So this one was something where you might have some dust. This one doesn't have dust. So you can see that the upper limit is very, very high as compared to this. So it's not useful. But on the other hand, you can provide constraint because it means that this galaxy cannot be a high redshift galaxies, while it might be if we consider only this range. So several other ones, you see H beta, O3, H alpha, etc. The Lyman break. Well, you can move, and I had at this time 173. Now we have CEERS data with several thousands data. So let me move now to the next point. We get all this data from CIGALE by fitting CIGALE. So you get the line flux. We can fit the lines individually, plus the continuum. But we want to check first that everything is okay. So the first thing I did is to compare with another estimate using the LIME software that was from Vital Fernandez et al. There is a paper about it. And the color codes, the wavelengths from blue or UV. There is Lyman alpha below, I think. to the red one, and this is what CIGALE estimates. So it's not true measurements, it's fit to the data. So that's related to the models fitting the data. As you can see, there is a good correlation. With this specific estimates, there is a difference here, but about 20%, which might due to the different way we estimate, or maybe there is a bias in one of these things here. So that's 0.8. And you still have the here with crosses, the other AGN lines. So you have a good correlation here. For some of the objects, we also have gratings, so a much better spectral resolution. And I did the same job. I compared the flux measure through the modeling of the lines. So this is directly from the lines, not the fitting. Well, it's the fitting of the lines, while this is from the spectrum itself. And you can see that you have a good correlation down to this value here. And this value here is 3 sigma of the background around each alpha. So you're able, or we are able to estimate the flux of these lines, well, different range, different lines, down to approximately 3 sigma of the background. After that, you start to get lost, and you're not able to estimate the fluxes of the lines. Once you have the lines, of course, you can estimate metallicities directly from the lines. Here, I have the metallicity estimated by CIGALE. So, of course, it uses the lines, but not only the lines, all the photometric and spectroscopic information. And using the same objects in 2 papers, Nakajima et al. And Sanders et al., I can compare the metallicity. Sanders and Nakajima use estimate metallicity using the excitation temperature from the O3 lines. And so these estimates are very good here. And it's calibrated approximately until this region. Below, there are no calibration, and it starts to become more difficult. In the range where Nakajima and Sanders had calibrations, we have a very good agreement, as you can see here, in 12 plus like OH. Below, we start to have a disagreement. It might be increasing or might be a different range, we don't know. But still, we are not sure that even Sanders and Nakajima have good metallicity here. And if we compare everything here for all the galaxies, so I put all the dots, comparing everything to everything, this is the average. The black dots are from CIGALE, and you have the other ones using different line ratios here. And you see that you have, for a given average metallicity, you have a very large range of metallicity. So again, well, you need to be careful depending on what calibration you use. The metallicity you will get is different. Using rolling average here, you see that the black lines is CIGALE. This is 1-to-1. It seems that CIGALE is more in line with what Nakajima estimates. You see this reddish part, and it's more different from what Sanders get. But of course, we don't know which is the good one, but we can still say that we have some estimation which is valid over quite a good range of metallicity, and in agreement with what you would get using this line ratio and Nakajima's calibration. So again, I use CIGALE. I use CIGALE, and I have my sample. Just to have an idea of what happens, I tried several star formation history. One is a delayed SFH and a recent burst at the end. So you have the parameters. So the age of the main population is can be vary a lot, because at high redshift you expect to have a main population which is very young. Then you might have a burst with different strengths. I use also periodic SFH, which is just different peak of star formation, different events separated by quiescent times, and I checked the difference between the two of them. I don't have time to show you what are the differences, but most of them are in agreement. I don't see any trend with a different SFH. That suggests that whatever result I get are not strongly dependent on the SFH, I assume. Then SSP, I use Brusel-Cherrieux and Chabrier. New nebula emission from Tolle et al. That we included in CIGALE. Dust attenuation, I use the one from Denis that I mentioned before, coming from ALPINE. So it's fixed to these values. And finally, the dust attenuation law, I just modify the polar slope, not expecting to have a UV bump at large redshift, even though we can see some galaxies with maybe a bump, a UV bump. Using this information, I estimated the stellar mass, as you saw before, and you see that depending on the spectroscopic UV slope beta, I directly measure this from the spectrum, not from CIGALE. We have the lower stellar mass with blue UV slope, then an intermediate, and the larger stellar mass with a red UV slope. This is in logarithm here, which explains that it's not center. But so this is something that you explain. From what information I have, the lines, I can estimate the mass of metals and the dust mass as we saw. And I try to check how this evolves for every single object as a function of the SSFR and the age of the universe. The blue is related to the mass of metals and the red to the mass of dust. All of them are normalized by the stellar mass. And you can see, you have the redshift here, that we see that the two of them seems to decrease with the redshift, especially the mass of metals, which is going down. It's less obvious for the mass of metal, but we might have some selection effect at play here. Same thing here as a function of SSFR. We have two different trends. Well, no, about the same trend, but two different levels, which can be seen. And you see that for both diagrams, we have data here for the dust to stellar mass ratios that are well below the other ones. So that's this type of objects that we'll try to understand and explain here. Let me go back to this. So this is the main sequence. Well, it's just to check that everything is okay. This is the main sequence modeled by Spiegel et al. As a function of redshift. That's not 14, 4 to 12 here. And you can see that, well, we are more or less in agreement with what you expect, given that we might have different way to estimate the stellar mass in the SFR, but we're not off by a large number. And again, you have the differences with the betas UV slope. So if we compare that to the ALPINE that I presented before, so I'm sorry it's not very good quality, I just superimposed to one. We observe the same main sequence or prime sequence here, but we do have this galaxy here that we didn't have in the ALPINE sample. And that's the one I'm looking at, and I will try to understand what are these objects. So to do that, I forgot. I dubbed these galaxies with extremely low dust attenuation. So that's the name GELDAS that is here. And there are this symbol here that is Y up, I think, as a symbol, is where you have these GELDAs with different trends in this A5V versus log Mstar diagram. So this is Burgarella et al. It doesn't seem to match this relation. And the one I estimate from this data is this one. This is just a mathematical effect because we have logarithms. It doesn't go down like this. But still, you see that it's very different. And the redshift range is shown here in three ranges. And you can see that the highest redshift galaxies are all in this GELDA range, except one. They have a low dust attenuation, below 0.5, a low dust mass, below 10 to the 9. And we have 49 objects in this range that I call GELDA, as I said before. If we put now the same object in this dust to mass ratio as a function of metallicity, they are here again. These are the agents. And you see again that we have in this region the highest redshifts with a low mass of metals. You can see that in the diagram. The red are the highest redshifts, above 8.8 in redshift. And if you do some statistics, you see that most of the high redshift galaxies above 8.8 are here, while you have only about 22% of the other galaxies below 8.8 that are here. So maybe there is an evolution, and most of the galaxies at high redshift, at very high redshift, could be very low dust attenuation. It's not a surprise, obviously, but still it's good that we can check that it happens. Because we have all the spectra, I stack the spectra of these 49 GELDAs, and I get this spectrum with the UV slope. We might have here the C3 and some lines, but we do detect each beta, all 3 lines, each alpha, and we have all this information. So using this, this is O2, I think the doublet. That is, well, maybe there is something like C3, but it's below the uncertainty. So we have a spectrum which is very well characteristic of starburst galaxies, starbursting galaxies. And this is the line ratio that we get. So we have a very blue UV slope. The size of this galaxy estated at 2 micron approximately is very small, and even smaller, so about 0.4 kiloparsec, and even smaller for these GELDAs. So they are probably very dense, H2 dominated, high luminosities, low mass. And using this line ratio here, the Balmer decrement, it's consistent with 0 dust attenuation. So if we want to put these galaxies in this type of diagram, Mdust, Mstar, so this is from distance on gamma HR plus, we would like to populate this area at low mass to see what happens and when we could have this first dust grains. And of course, hopefully we would find this galaxy, this GELDA galaxy in the same range. So that's the same diagram. You have here stellar mass, dust mass. We wanted to populate area, and apparently we won. We have the GELDAs here. Sorry, the GELDAs here. The symbols are here, and you see a trend here with some transition maybe, and another type of galaxies here that might be a clump or a parallel one. So looking at this, it seems that we might have some galaxies appearing here at the same dust mass, stellar mass, with the right range, and maybe that indicates that something different happens in galaxies here and galaxies here. So let me move now to models. We have the same parameters here. From Stock et al., we have the ISM dust here, the stardust here, and we expect to have some transition here at some point that is around 8.5 in logarithm of Mstar, meaning that the galaxies mainly have stardust here and ISM dust here. And when we look at models, Grazzani, Mancini, Esmerin et al., we confirm that this happens like this. We do have this transition in this mass range. And when I said later now, this is what where we are now. So we have these galaxies here with very low dust mass, very low dust attenuation observationally. And at redshift larger than 8.8, about 83% of these galaxies are GELDAs. That means that they have a very, very low dust attenuation consistent with 0. And this is very different. At low redshift, it's only 20%. So we might have a transition at redshift approximately 9. And because we have less attenuation, we will get, of course, higher UV luminosities and blue UV slopes that contains young and metal pulsars. Maybe at redshift larger than 9, this is just speculation. I don't have any information about it. We can have population-free stars in these galaxies. This is Maisie's galaxies that you might know. So these GELDA galaxies are stardust galaxies, and that may be at the origin of what we observe in UV bright galaxies. So we are almost at the end. I give you my first conclusion. So we fitted 173 spectrum with a new version of CIGALE, which is available, but only for NIRSpec, but we're still working on it. We identify what we call GELDAs in this redshift range. And this is based on only a total of 1,300 galaxies, if I remember well, from CEERS. But we'll have 10,000 galaxies with CEERS. We already have 3,000 of them already observed in the UDS field. So we'll, of course, try to check if we get the same type of information. On the 3,000 that we have now, we do get the same type of things. They are dominant at larger redshifts. They might explain the UV excess of galaxies. You have other possibilities that are mainly related to dust, IMF, and star fusion efficiency. And in the cosmos field, it's very interesting because we'll have the CEERS data, PFS data from the ground that will give you some better spectral resolution in optical and UV. VLT moons, same thing. And using all this data, we can be able to characterize galaxies in the universe. And maybe because we have UV restraint, try to identify low metallicity and population free. And we'll try to work on models as well, because the models that we use, Buzol and Charlo, might not be up to date. And we'll try to develop new models specifically for these low metallicity galaxies. Just a final word on CIGALE speed. So that's something I presented at SPAE. So probably you read in some papers, for instance, this was from Vigilo et al., that one of the main advantages of machine learning is the time necessary to derive the desired results. And there is a huge improvement on time cost moving from acidific cone to some neural network. So I was wondering if these claims are fully tested and confirmed. So what I did is I checked on the same sample, which was a sample in Cosmos. I had 5 bands from SDSS, from Euclid bands, or LSST band, whatever. And I checked the differences that you get. So this is to estimate redshifts. So the number of, the percentage of outlier, if you want, is given here with the sigma mad here. The number of objects fitted, so 63,000, 75,000 here. The number of models, of course, here you don't have models, but you have some training before that is needed. That is quite large for this CNN or deep learning neural network. And the time is given here for the inference only. So normally you should add this to get the total, except that this one is only once. For CIGALE, using my computer, the one I have here, or a normal server with 20 cores, I estimated the redshift in 15 minutes for this 75,000 objects with 500,000 models. And here on this computer in 9 minutes. LeFar would use 4 hours on 12 cores. So this is for photometric redshift, but CIGALE is not designed to make photometric redshift. It can, but it's not the best one. Then I tried to estimate parameters. So stellar mass plus 5 other parameters like the dust attenuation, the star formation, etc., with the same type of comparison. So you have the outliers here. And of course, because CIGALE is more adapted to this, you have a fraction of outliers, which is well below. The training, there is no training in CIGALE. You still have some training. I assume it's the same than before. And then the time that you would need. So I assume it's the same because you can estimate everything. So 15 minutes, 1 minute, which is, of course, below 1 minute is almost immediate. But with CIGALE, on my computer here, I have 3 minutes. On Vulkan, 2 minutes. LeFar, I don't know. Prospector on 3,000 cores would use 24 hours. So just this to say that we have very good quality estimate and very fast. The quality is shown here. well, you shouldn't look at what happens here because this is a star formation rate, and well, below 1, of course, it's badly estimated. But for 70,000 objects or 1 million objects, you can do that very fast and get some nice information. So, of course, this is something you can find. I said that it's CIGALE is the fastest spectral, SPD is a spectral photo energy distribution fitting code in the world. I didn't check systematically, but at least in the previous one, it is. Thank you. I hope I'm in time. Yeah.
Thank you, Denis. Thanks so much. Okay, so we have now some time for questions. So you can, you can actually just simply open your mic and ask. So I was wondering, if this business that you were mentioning of the IMF, when you're doing this analysis of these GELDAs, how much of it would be if you consider variations of the IMF? In principle, your original fluxes from the populations will change, so that will affect also the derivation of the beta, etc. So will that affect also your analysis?
Well, so far we didn't have this analysis done on this sample. Ambra and Nani in Poland working on CIGALE and with a new BC03 model, top-heavy BC03 model, did some analysis. It changes a bit and it allows, if you remember, or maybe I can share again.
Yep.
Yes. Can you see?
Yeah, we can see the screen. Yeah.
Okay, so let me move to the relevant plot. Okay, this one, for instance.
Mm-hmm.
So this use Chabrier, but so with this new top-heavy model from Visual, actually, it seems that they are able to lower the slope here. This means that these objects would get a little bit below, and they would be able to get more easily these objects. But one here are still out of reach for this type of models, except if you have some specific assumptions on what happens in the outflows and inflow. Otherwise, let me check where is the other one where I had, yes, here. Other one, the range that we have is not large enough. You see top-heavy is red, Krupa and salpeter, red and blue, and so you see you have a small difference. So if you assume a very extreme IMF, you might get able to get down here, more top-heavy, but right now it's not enough. You're not able to explain dust formation using this type of model at least. The spectroscopic analysis will be carried out, or it's being carried out now to try to explain using the line emission, and so maybe better constrain the IMF from the line that we have in the spectrum to see if that changes anything. But from this analysis and from the one that Nani and the other people made, it's not possible right now to do anything related to that.
Okay, that's what I was wondering. So basically, once you have a proper characterization of the emission lines, in principle, you can constrain it better.
Yeah, and this we will have, of course, with the spectroscopic information. Excuse me, one second.
Sure, no worries. Yeah.
Okay, sorry.
So yeah, no worries. So one other thing is, when you're measuring the properties of these GELDAs, would you imagine these systems appearing at lower redshift? Like, let's say intermediate low redshift, because you're now presenting this from a sample that is basically going from redshifts, I don't know, like 4, 5, 8, 10. So if you go down to, I don't know, redshift 1, would you expect a substantial number of galaxies having similar properties than the ones you're considering here?
Yeah, actually, yeah. I started at redshift 4 because I thought that, well, I would like to study the first phases of dust formation, and I wasn't expected to have so much of these galaxies with these type of things. However, well, we might have in the redshift universe, at redshift 6 or 4, local bubbles, let's say, where the elements were not formed before, and so you form the first dust grain at this time. If you go below redshift 4, it may be more and more difficult because the AGM itself start to contain dust grains, if I remember well, and I'm not sure we would be able to get them, but I didn't check. That's something I plan to check. That's a good idea. There's a good point about it. I mean, for these objects, for the GELDAs, the detections with ALMA are almost impossible.
Mm.
If we go to low redshift, we might get the boost because of the shorter distances, and maybe try to detect something to confirm or not if we have this type of information. But well, a priori, I don't expect to have this type of galaxies at low redshift. Even here, maybe some of them are not fully correct, as are uncertainties. But it might be that we have population 2 here and maybe population 3 here. So, but we don't know actually.
It would be interesting. I mean, to see, because as you say, possibly this would be a minority of objects at lower redshift, but in principle, the characterization where those live would be interesting. Thank you. Yeah.
Sorry again.
Yeah.
I'm sorry. I have someone who has to leave. And I have to open the door of the car outside. Okay, it's good now. Sorry.
Yep. So any other questions from the audience here?
Yeah, actually I have a question if there is time.
Sure, please.
Yeah.
So Denis, I was wondering, when you have the transition from stardust to ISM dust, would you expect to have a different extinction curve, for example, or different emissivities for the dust? And to what extent this could be explained the different beta load that you get for the dust?
Yeah, that's an excellent question. I have been wondering this, and I have several people. There are predictions, but the predictions are very model dependent. What people say, well, actually, Erki Rashta said, is that we expect for this type of stardust galaxies, if I remember well, to have flatter dust attenuation curves. However, he told me that this is really strongly model dependent. What I observe, because I tried to check this, of course, is that I have something with, in CIGALE, we have a slope delta that change the dust attenuation with respect to causality. And it seems that for these GELDAs, we have something which is close to 0, which means that's almost a pure causality curve. However, the uncertainties are very, very large. I mean, that's the average is all around 0, but the uncertainties are very large, so I cannot say. So asking several people, they all told me, well, we expect this. Other people told me we expect this, and it was not the same this. And also the uncertainties on the models were very large. So it would be very nice to initiate some type of modeling specifically by thinking about it and check what we can get, because we will have the dust attenuation low, or we can derive the dust attenuation low if we have good enough data. And JWST plus the ground-based telescope like PFS, MOONS, will provide this type of information very nicely. But right now, it's not possible to get any strong constraint from models, unless you have some.
Yep. And if I may ask one more question,
Yes.
I was also wondering, exactly because those galaxies are so dust poor and there is very strong UV, how much would you worry about stochastically heated dust and the applicability of the Drain and Lee models in these very tenuous dust environments?
Well, that's the point. I mean, the galaxies are very small. As you saw, about 300 parsec or so. And they are very young, first because they are in high redshift, but also because they are younger in an absolute wave. So what I find is it seems that the galaxies are more, no, not the galaxies, the stars are more clumped. So you might have big H2 regions. And depending on what you assume on the distribution of dust around these clumps, if you have clumps, you might have different things that are related to what we just said before, the dust attenuation law, etc. And also, of course, you can have different position, but because they are so small, they are unresolved, mainly unresolved by JWST. So you get everything at the same time. And so you have an integrated view of these small galaxies when you get to any redshift from 4 to 11. So modeling inside the galaxies could be a very nice thing to do. And of course, that will mean that we need to assume what is the distribution, what is the morphology, stellar and dust morphology inside the galaxies to check. But well, that's what we do when we try to estimate the dust attenuation law, if I understood well. I mean, you try to model what is the morphology of these two components and try to check what you expect at the end. In my case, I assume that I have something very simple, and I'm not sure it's correct, of course. But as you can see, yeah, you still can see it. All the models, I mean, I've been exhaustive here. All the models seem to suggest the same transition approximately as stem cell mass. You have some weights, but everything seems in agreement. This transition here is mainly due to the metallicity. That's the result from Mstar et al., quite old. And you have dust crowns here, you don't have here. So the metallicity is a leading parameter. It's not a stellar mass, but still, of course, you have the mass metallicity relation and you have a link. But well, if these objects are confirmed, we really need to model them and to understand what we have in these objects. And if we do, we might have some good information on these first phases of dust formation in the universe. Did I answer your question?
Yeah, the question was a bit more general. I mean, like how applicable the Denis and Lee models are in extremely low extinction galaxies. Not necessarily the GELDAs, but in general, like very low extinction galaxies where you may have a significant component from stochastically heated dust, or the dust may not be in total thermal equilibrium.
Yeah, that's the point. I mean, if you look at what I showed before, well, actually, because we have such a small amount of dust in the galaxy, what model you use is not very important. Let me find one. Yeah, this one. So even if you use a modified black body or another model, you won't be here. So the contribution from this part here is not very constraining for what you get here. So that won't change a lot if you change another models. And well, I'm not sure whether it's applicable, of course, with any models or whatever models you assume for the dust emission, but it will not change at all what we have here. For the other ones, I agree, but here I'm not sure it's very important. I just put this because I have these upper limits, which are mainly, as you can see, very high for all the objects. Maybe I can zoom a bit. Yeah, you see, all of them are very, very high, so they are not very important for all these GELDAs. This is a selection of GELDAs that we have here. So in this case, the impact I expect is not strong, or it's even not strong at all. Okay.
Okay. Thank you. So I think we are out of time. So thanks so much, Denis. That was a very nice talk. And yeah, we will be posting this on the YouTube channel. So thank you. Thanks so much.
Thank you.
Yep.
Bye.
Take care. Bye-bye.